Alright, so in all of the memory management schemes that we have talked about so far, we have been assuming that the entire process needs to fit inside the main memory in order for the process to execute. However, with demand paging, we are now going to relax that assumption. We will now allow only a portion of the process, the executing process, to be resident inside the RAM or the main memory. Essentially, that portion of the process which the CPU currently needs for its execution would be inside the RAM. The rest of it can be on the hard disk. Further, with this demand paging scheme, we will see that because the entire process does not need to be loaded or fit inside the RAM, we can now allow processes that can potentially be bigger than the physical RAM to execute. So for example, it is possible that your computer has only 16 GB of RAM, but you would still be able to execute a process that may be 32 gigabytes in size, because all of it does not need to fit inside the RAM at the same time. So how are we going to do this? Well, here are the key ideas. So in demand paging, we are going to treat the hard disk as a backup region or as a slower extension of our main memory. So imagine that the hard disk is a much larger but a slower form of RAM or main memory. So recall, just as the TLB was a cache for the main memory, now the main memory will act as a cache for the hard disk. So initially, by default, when we start the execution of process, the process would initially be stored entirely on the hard disk. Now, as the process begins execution, those parts of the process which are needed to execute inside the CPU, those would be cached in the main memory or the RAM. And the portions of the process which are no longer needed for execution, they can be swapped out from the main memory to the hard disk. So essentially, in demand paging or in virtual memory, the operating system is presenting us with an illusion that the size of our main memory is no longer limited to the physical size of the RAM. However, it is now including the size of the RAM as well as the size of our hard disks in the computers. By presenting this illusion, the virtual memory is able to present a lot of useful features for us. So for instance, now that a process does not need to fit entirely inside or inside the RAM, or it does not need to be present entire in its entirety in the RAM or the main memory, we can now execute processes that can be larger than the size of the physical RAM in our computer systems. With virtual memory now, that only a fraction of a process needs to be inside the main memory, we can actually fit more processes concurrently in the same amount of RAM. So the degree of multi-programming will go up significantly. And finally, note that we only need to load a fraction of the process from the hard disk into the main memory to begin its execution. So this loading time of the processes before execution will significantly go down. So this is a quick summary of demand paged virtual memory. Most modern operating systems that we use, they all support virtual memory. As we will see moving forward, virtual memory also uses paging and page tables. However, now the page table entries will tell us whether a given page is in the main memory or is it in the hard disk. Alright, so let's now talk about this demand paged virtual memory in some more details. So we have already seen that the demand paging uses main memory as a cache for the hard disk. We have also seen that virtual memory still makes use of page tables, and the information stored in the page table will now additionally indicate whether a given page is stored in the hard disk or is it present inside the main memory. So the way this information is stored is, let's say we have this example page table, and let's say this first column here, this is the page numbers, and let's say this is our frame numbers from the main memory. So for example, let's say this page 0 of our process is, let's say, stored in frame number 10. Let's say page 1 is stored in frame number 20, and let's assume that this page number 2, this is currently on the hard disk. So to represent this fact that page number 2 is on the hard disk, not inside the main memory, we will now add additional column here in the page table, which is basically a valid bit. So if this valid bit is 1, it means this entry is valid. This particular page number is present inside the main memory. However, if this particular page number, let's say page 2, is in the hard disk, this valid bit would be invalid. This would be 0, and then this entry for the frame number would be empty. So this indicates that page number 2 is in the hard disk, not in the main memory. Whenever a certain page is brought in from the hard disk to the main memory, the operating system will update the page table and also the corresponding valid bit. So for instance, let's say we bring in this page number 2 from the hard disk, and let's assume that it is stored in this frame number 30 in the main memory. So at that time, the operating system will update this frame number, and also it will change this valid bit from 0 to 1. Note that for efficiency reasons, it is important that our demand paged virtual memory systems, during execution, the executing process is vast majority of the times referencing to the pages which are present inside the main memory, as opposed to referencing the pages that are present on the hard disk. If this is not true, if the executing process keeps referring and frequently accessing to pages that are on the hard disk, then the performance we'll get with our virtual memory systems would be terrible. So why is that? You would recall that the time it takes to access data that is stored on the hard disk is several order magnitudes greater than the time it takes to access the data stored in the main memory. And therefore, it is important that during execution, the executing process vast majority of the times is accessing pages that are present inside the main memory. Having said that, fortunately for us, a vast majority of programs in execution, they exhibit locality. Recall, we talked about the 90-10 rule. So roughly speaking, this basically states during execution, 90% of the time processes are accessing just 10% of their address space. And therefore, to make this virtual memory scheme work, we only need to make sure that this 10% pages or these 10% addresses which the process needs for its execution right now, those are present in the main memory. The rest, 90%, can be on the hard disk. Now this 10% of addresses or instructions that an executing process is using at a given time, this will evolve and change over time. And so over time, as new addresses or new pages are needed, once in a while, the executing process would reference to an address that is stored currently on the hard disk. So for such references, once in a while, we will need to load pages from the hard disk into the main memory. But because of locality in our program execution, once a page has been loaded from the hard disk to the main memory, the process will be using this page for a while. And all the subsequent accesses and references to this page will be efficiently answered. And any old pages that the process no longer needs, they can be swapped out of the main memory and they can be stored back on the hard disk. So this is really the key idea. Locality in execution of our programs make demand paged virtual memory systems work efficiently. This slide pictorially illustrates the demand paged virtual memory system. So this is our main memory or RAM here. This is our hard disk. This is the page table for a process. We can, for simplicity, assume that the page table also resides in the RAM. However, for virtual memory also we can use TLB caches. And this over here, this is the process virtual memory. Essentially what this is showing is the virtual memory address space of the process itself is divided into several pages, just as in the paging scheme earlier. And this page table is telling us which of all of these pages are in the RAM and which of these several pages are in the hard disk. So for instance, this particular page is stored here in the main memory. Similarly, page in this entry of the page table is stored here in the main memory. However, this particular page, this is not in the main memory, this is actually stored on the hard disk. So the page table tells us which of these several pages are in the main memory and which are on the hard disk. During execution, if the executing process tries to access this entry corresponding to a page which is on the hard disk, this will result in what is known as a page fault. So page fault basically refers to the event where executing process is trying to access a page that is currently on the hard disk, not in the main memory. So page faults are basically handled similar to how traps are handled. A page fault will trigger a trap in the operating system, so we will suspend the executing process that has caused this trap, the page fault, and the suitable trap handler for servicing this page fault would be invoked. So this trap handler will essentially fetch this page from the hard disk and bring it somewhere in one of the available frames, let's say over here in the main memory. It will then update the page table accordingly, and once the page is available in the main memory, the page table has been updated, we can resume the process that had caused this page fault. Anytime an executing process causes a page fault, the process will be stalled until the page can be fetched from the hard disk and brought into the main memory. Recall, accessing hard disk, bringing data from the hard disk is much slower as compared to fetching the data from the RAM, the main memory. And therefore, page faults can cause a significant delay in the program execution, which is one of the reasons that we like these page faults in our processes to be as rare as possible. The procedure for serving the page faults is transparent to the executing process. The executing process does not know whether a given page is currently in the main memory or whether it is being fetched from the hard disk. The executing process will simply experience more delay for instructions that cause page fault. That will be the only difference from the executing processes perspective. So we have talked about many different memory management schemes, and we know that not all of them require the entire process to be loaded in the main memory all the time for execution. The common thing, however, across all of these schemes is that the entire process must be resident in the hard disk. But the question remains, for a given process, when to load a given page into the main memory, and also at any point in time which pages to load in the main memory. We are going to try to answer these questions for various schemes over the next two slides. So the first possibility for loading a page to the main memory is at the process start time. So this means when the process starts execution, at that time we load all the pages belonging to that process from the hard disk into the main memory. So the main advantage of doing this is first, every page is loaded in the main memory at the beginning, so there would be no page faults. And second, it is easy to determine when to load. Everything is loaded at the beginning, so there is no complexity for later. However, the main downside of this approach is that the size of the processes is limited by the size of our physical memory. The processes must fit entirely into the main memory, and they should be loaded in the main memory to start execution. The second possibility is that we let the application programmer decide when to load a given page into the main memory and when to remove the page from the main memory. This is essentially what is done in overlay programming. In overlay programming, the programmer manually divides a program into various self-contained object code blocks. These code blocks are called overlays. These overlays are themselves organized in a tree-like structure, and there is an overlay manager. This overlay manager is responsible for loading the required overlays from the external memory, let's say from the hard disk, into its destination region when it is needed. Now this overlay manager, this could either be part of the operating system or it could also be part of the overlay program itself. The nice thing about overlays is that they do allow the process's virtual address space to be larger than the actual physical memory which is available in the system. However, the main downside is writing an overlay program is typically difficult and is also error prone. Nevertheless, the overlay programs remain a useful tool in the embedded systems. Many low-cost processors that are used in the embedded systems, they do not have a memory management unit. They do not have capabilities to support demand paging or virtual memory, for instance. So for such system, the overlay programs are an excellent alternative to virtual memory. Besides this, many embedded systems are actually real-time systems. So they need real-time guarantees about execution of processes or certain tasks. So for such systems, overlays, they provide better time guarantees as opposed to virtual memory or paging. That's another reason overlays are relevant in embedded systems. Now, having said that, we are not going to go into details of overlay programming because that is beyond the scope of this course. Now, the third alternative to determine when to load a page is demand paging or pure demand paging. So the pure demand paging basically says that by default, all the pages of the process, they are staying on the hard disk. They rest on the hard disk. The operating system will load a page from the hard disk into the main memory the first time when it is referenced or needed. So if a page is never referenced, then it will never be brought in from the hard disk into the main memory. This is pure demand paging. So in pure demand paging, there must be at least one page fault corresponding to a given page for the page to be loaded from the hard disk to the main memory. So let's assume this is our RAM over here and this is our hard disk. We have a process P1 on the hard disk, and let's assume this process P1 has only 3 pages, and we want to execute this process P1 in the RAM. So the first time when it starts executing, let's say we bring in this page 1, the first page of the process, into the RAM. Let's say after some time the process P1 creates a page for it, makes a reference to this page 2. So there is a page fault because this page 2 is currently on the hard disk, so this page 2 would also be brought in to the main memory. Subsequently, let's say later on there is a page fault for this page 3. Now at that time we will bring in this page 3 also into the RAM. Now let's assume that right now there is no room for this page 3 in the RAM, right? There was only room for these 2 pages. So in this case we may need to evict some of the old pages from the RAM to make room for the new page. So let's say we evict this page 1 here, and then we bring in page 3 in its place. This is a quick summary of how demand paging would work in general. Recall, we have already talked about this term called page fault. More formally, page fault is actually an interrupt or a trap that is caused when an executing instruction references a page that is not currently in the main memory but on the hard disk. Page faults are handled in our operating systems typically as an interrupt. Whenever there is a page fault caused by the executing process, this will raise an interrupt or a trap in the system. The executing process would be suspended. So that's why the process must give up the CPU. And now the operating system will invoke the corresponding trap handler for servicing the page fault. As we have seen, the trap handler will basically load the necessary page from the hard disk into the main memory, update the page tables, and then we can resume the faulting process. So that's a quick summary of demand paging. As we have seen, purely demand paging approach will create at least one page fault for all the pages that are used in the process execution. Now this may not be necessary, especially if you are using some kind of pre-paging. So pre-paging basically says that many times operating system may be able to predict or guess which pages the process will need in advance. So instead of waiting for the process to create a page fault for those pages, we may be able to preload those pages in the main memory, so that when the executing process in fact references those pages, they will be found in the main memory and we will avoid the overhead of a page fault. For instance, when we are starting a process, we may be able to guess at the beginning what are the set of pages that the process will need. If our guesses are right, then pre-paging has potential for allowing a better overlap between CPU and IO subsystems. So essentially what we mean by this overlap is, while the executing process is currently executing the processes, the pages that are already in the RAM, in the background we are fetching the next set of pages that would be required by this process. So this is an example of excellent CPU and IO overlap for the executing process. So this overlap increases the resource utilization in the system, and it also improves the performance or execution speed for the executing process. However, it is not always easy to predict the next set of pages that a process may need, and incorrect predictions come at a cost. So for instance, let's go back to this example. So let's say process P1 is executing and it currently has these pages 1 and 2 in the RAM, and page 3 is on the hard disk. So while executing this instructions on page 2, let's say the operating system predicts that this process will next need page 3, and so even before page 3 is accessed, we prefetch this page 3 and bring it into the RAM. So let's say we evict this page 1 because there is no room for keeping all 3 pages in the RAM. So we evict page 1 and bring in page 3 here in its place. If this prediction turns out to be wrong, it turns out that the process, in fact, due to some branch, maybe some unpredictable, unforeseen branch, this process would next, let's say, require page 1. So page 1 was already present in the main memory. We evicted it to bring in this not needed page 3. So this will actually increase the page fault, which would otherwise not have happened. So it is possible that incorrect predictions may be removing some useful pages from the main memory. And needless to say, we are wasting the memory bus bandwidth in fetching data which was not needed. Note that incorrect predictions will not affect the correctness of the executing program. It will only incur page faults, which will slow down the execution of the process. In summary, pre-paging is a useful technique. However, it is not always easy to predict correctly the next set of pages that would be needed, mainly because of branches and other similar uncertainties in program execution. Here is a quick summary implementation of demand paging. Recall, in demand paging, the page table was expanded to include a valid bit. So corresponding to every page, we have a frame number and then there is a valid bit, 3 fields in this page table. So if the page is in the main memory, recall that for a given row, if the page is in the main memory, we'll have the frame number and the valid bit would be 1. However, if the page is not in the main memory, if it is in the hard disk, then corresponding to that page entry in the page table, the frame number would be empty and the valid bit would be 0. So this means 0 is invalid. It means that the page is on the hard disk. So here is how the demand paging would work. By default, the entire copy of the program would be stored on the hard disk. So in this discussion, we are not assuming any network access, and therefore the program must be completely present in the hard disk. Otherwise, you cannot execute the program. Now, as we have seen, the valid bit in the page table will indicate whether the page is in the main memory or is it in the hard disk. If the valid bit is 1, it means that the page is in the main memory. If it is 0, it means that the page is on the hard disk or it's an invalid address. When accessing a page table entry, will determine whether the page is in the memory or not. If the page is in the memory, then no problem, we can continue accessing the page as usual. However, if the page is not present in the memory, then this will cause a trap to the operating system, which is a page fault. In response to the page fault, these steps would be followed to serve this page fault. First of all, the operating system will check whether the address which has faulted is a valid address or not. If so, then we will proceed with these steps. If not, if it is not a valid address, then the process may be terminated. So let's assume that the address is valid. The first thing we need to do for bringing in this new page from the disk to the main memory is make room for this new page in the main memory. So let's assume that this is a portion of our RAM and the executing process has access to these three frames. So let's say these are frame 10, 11 and 12, and let's say page 0 is stored here in frame 10, page 1 is stored in frame 12 and page 2 is stored in frame 11. And now as a result of this page fault, let's say we want to bring in this page 3 from the hard disk. To make room for this new incoming page, we'll need to evict one of these existing pages P0, P2 or P1 from the main memory. Now which page to evict is typically determined by page replacement algorithms. There are many different page replacement algorithms that can be used. We will talk more about these page replacement algorithms later in this unit. So for now, let's assume using one of the page replacement algorithms, we somehow choose this page 1 for eviction. So we'll remove page 1 and we'll bring in this new page P3 in its spot. So the way this will work is we will invalidate the entry for this page 1 in the page table. So here this is the current state of the page table for this example. Let's assume that using one of the page replacement algorithms, we selected this page 1 for replacement. So we'll evict this page. The way this works is we'll copy this page from the main memory into the hard disk, and then we'll update its entry in the page table. So this page table shows the current state of process. So we'll update this entry for page number 1, which was currently in frame number 12. But now because we have copied it on the hard disk, we'll change this valid bit to 0 to indicate that this page number 1 is no longer in the main memory, and we will also remove this frame entry, so this will be blank now. So page 1, let's assume, is gone from here. Now frame 12 is available. Now we will start loading this new page P3 from the hard disk into the main memory. Note that this is an IO operation, so this will take some time. This will take a while as compared to the CPU execution speed. So while this page 3 is being loaded or copied from the hard disk into the main memory, in the meantime, to keep the CPU busy, we will context switch and start executing some other ready process. The process that had caused the page fault has been suspended and it is now in the waiting state. Later on, when this page 3 has been copied into the main memory, the operating system will get an interrupt indicating that the page is now loaded in the main memory. At that point, the operating system will update the entry in the page table. So for page 3, we will update this entry. Now you see the page 3 is in frame 12. So under this frame column, we'll include frame number 12 and we will change this valid bit to 1 to indicate that page 3 is now in the main memory and not on the hard disk. Now once all of this is done, we can resume the execution of the faulting process from the instruction that had caused this page fault. At multiple points in our discussion of virtual memory, we have said that a page in the main memory which is no longer needed, or sometimes when we need to make room for a new page from the hard disk that is coming into the main memory, we can evict a page from the main memory. But what really happens to this page when it is removed from the main memory? An evicted page in a virtual memory system is typically saved on the swap space. So what is this swap space? So on Linux operating systems, we have swap partitions. On Windows, we have swap files. So it is the space on the hard disk where we keep these evicted pages from the processes in a virtual memory system. So you might wonder, why do we need this swap space? So note that the swap space is actually optimized for speed of access. The pages that were evicted out of the main memory for the executing process, they may be needed again in the near future, and therefore it is important that when they are needed again, the operating system is able to copy them quickly from the hard disk back into the main memory. So this will save time for the executing process. That is why the swap space is optimized for speed. It is organized and accessed differently from the rest of the file system on the hard disk. If for some reason there is no swap partition on a system, then the operating system typically creates a large file on the regular file system, and that file is referred to and used as the swap file. The operating system will store evicted pages and processes in that large contiguous swap file. Now typically these swap files are hidden files and they are managed by the operating system. If you were to accidentally delete a swap file for a process, the process will typically crash or terminate. Uh, if the operating system or the system is, let's say, running low on the swap space, or for some reason if we want to optimize the use of the swap space, we can do some simple optimization tricks. So for example, you would recall that a process typically consists of 4 segments. So we have the code section, the data section, the heap section, and the stack section, and then there is some room here for the heap and the stack to grow and shrink. So out of all of these, typically code section is not modified, and therefore this can be discarded. We can always reload the code from the hard disk directly, because we will have a copy of the code section on the hard disk in the file system. However, the other data sections, the stack, the heap, and the data, they can be modified. They might have been modified during the execution of the program, and therefore when the process is or a page is evicted out, these sections need to be stored in the swap space. So if the page contains data, we need to save the data so that it can be reloaded in the process. It belongs to if it refers to it again. Now note that if we have swap space or swap partition in our system, then a page of a virtual memory address space, it could be in one of these 3 places, right? So it could be in the physical memory or in the RAM, or it could be in the regular file system inside the hard disk, or it could be on the swap space, which is also on the hard disk. So in this case, the page table would need to be more sophisticated. It will need to store more bits or more information to tell us where exactly to find a page. Let's spend some time thinking about the performance of demand paging. Now, if you think about it, theoretically, it is possible that an executing process could cause a page fault for every instruction. So every instruction can theoretically access a page which is on the hard disk. Now this will lead to terrible performance. But fortunately, vast majority of processes don't typically exhibit this kind of behavior. Usually, processes exhibit a lot of locality of reference during execution. You would recall from your study of computer organization that during execution, processes exhibit 2 types of localities. They exhibit temporal locality and spatial locality. Recall, briefly speaking, temporal locality states that if a process during execution accesses a certain item or a certain memory address, it will tend to re-reference the same item again in the near future. Recall that the spatial locality says that during execution, if a process accesses a certain memory address in the main memory, then it is more likely to access the neighboring memory addresses as opposed to accessing random memory addresses far away. So because of these localities exhibited by our executing processes, demand paging does not perform terribly. It actually has a pretty good performance in practice. Let's now think about the performance of demand paging using some mathematical expressions and numbers. So for this discussion, we will assume that the probability of page fault, so the probability that an instruction, executing instruction, will cause a page fault is, let's say, P. We'll further assume if the page is present inside the main memory, then the total time it takes to access the memory is given by MA. So note that for simplicity, we are assuming that this MA includes any times for accessing the TLB caches and so forth. Besides this, let's say if the page was not present in the main memory, then the total time it takes to service the page fault, get the page from the hard disk into the main memory, and then perform the memory access is, let's say, given by PFT, page fault time. So given these assumptions, the effective memory access time would be given by basically the weighted average of the access time when the page was present in the memory and the access time when there was a page fault. So which would be simply P. So recall that the probability of page fault is P. So the probability that the page would be found in the memory is given by 1 minus P. If the page is found in the memory, then it will take time MA to access, as opposed to this, if there was a page fault, that would be with the probability p, and the time it would take to access the memory in this case would be given by the page fault time. So this expression basically gives the average memory access time in presence of virtual memory or demand paging. Now to get some perspective, let's assume that on an average the memory access times in a system are, let's say, 200 nanoseconds. So if the page is present in the main memory, we don't have to go to the hard disk, then it takes 200 nanoseconds to perform the memory access. However, if there is a page fault, then let's say to access the hard disk, load the page and do everything, let's say it takes 25 milliseconds. So let's plug in these numbers in the expression. So the expression becomes 1 minus p into 200 nanoseconds plus p into 25 milliseconds. So 25 milliseconds is 25 into 10 power minus 6. I'm sorry, not minus 6. 25 into 10 power 6 nanoseconds. Recall that a millisecond is basically 10 to the power minus 3 seconds, and a nanosecond is basically 10 to the power minus 9 seconds. That is why 25 milliseconds would be 25 into 10 to the power 6 nanoseconds. A few things to note here, right? So note that if there was no virtual memory, let's say the entire process was in the main memory, in that case the average memory access time would be 200 nanoseconds. With demand paging, because we have locality in our program execution, vast majority of requests can be satisfied from the main memory, but occasionally there will be page faults and we will have to go get the data from the hard disk. And therefore the average memory access time with demand paging would be greater than 200 nanoseconds. Now let's assume that for reasonable performance, we want the average memory access time for this virtual memory system to be only at most, let's say, 10% greater than 200 nanoseconds. So 10% of 200 is 20, right? So at max we want the average access time, the overall effective memory access time for this virtual memory system to be 200 plus 20, 220 nanoseconds, right? So basically we want this expression to evaluate to 220 nanoseconds. So the question here is, what should be the value of p? What should be the probability of page fault to make this happen in our system? If you work out and solve this expression for the value of p, you will find that less than 1 in a million instructions should create a page fault to make sure that the overall memory access times are at most 10% slower than 200 nanoseconds. If a greater fraction of instructions are faulting, then there would be a greater slowdown. So this example over here is intended to give you an idea about how rare the page faults need to be to ensure reasonable performance degradations due to the presence of demand paging or virtual memory. We have been talking about demand paging and virtual memory. We have seen that just as the previous paging scheme, demand paging also makes use of page tables. And just as the previous paging schemes, to make accesses to these page tables efficient and fast, in demand paging also we will use a TLB cache. However, with virtual memory, there are some extra steps that we need to account for while updating the TLB cache, which are summarized over here. Just as we have seen, the entire page table would by default be stored in the RAM. However, some of the entries, the page table entries which the executing process is using or accessing right now, those would be cached in the TLB cache. Updating or loading the values in the TLB cache can be done either using a hardware implementation, or this can also be done by some system software. In general, if the hardware is used for loading and updating the TLB cache, that would be a faster implementation, so it would be good from the performance perspective. But as you would recall, typically implementing hardware is also more expensive, and therefore the software choice would provide a relatively cheaper alternative to this, which would be somewhat slower as compared to the hardware implementation. In general, if we want to boost or maximize the performance and cost is not an issue, then we should use hardware to load and update the TLB cache. However, if TLB already exhibits a very high hit rate, and we are not bothered by occasional one or two misses. We can also use the system software implementation to load and manage the TLB cache. Regardless of what implementation we are using, here is a summary of steps that will take place for accessing and updating the TLB caches. If the valid bit for an entry in the TLB cache is set, this indicates that the page is present in the main memory. This is not going to be a page fault. So essentially what this means is, on a TLB hit, we can directly use the frame number which is stored in that TLB entry and access the memory. There is no page fault. However, if there is a miss in the TLB cache, then the page that we are looking for, it may or may not be present in the main memory. We will know for sure only after accessing the page table in the main memory. Therefore, on a TLB miss, we will access the page table which is stored in the RAM, and we will check whether the page that we are looking for is in the main memory or is it on the hard disk. Recall, we have already seen earlier how the page table entries indicate whether a page is in the main memory or on the hard disk. After accessing the page table in the main memory, if it turns out that the page that we're looking for is indeed in the memory, then we are in luck. We just need to bring in this associated page table entry from the page table to the TLB cache. So to do that, the operating system will either find an empty location in the TLB cache, or if the TLB is full, the operating system will find an entry in the TLB cache which can be replaced to bring in this new page table entry. Once the TLB location is identified, we can simply fill in that location with the new page table entry. However, if after checking the page table in the main memory, it turns out that the TLB miss was caused by a page which is not in fact in the main memory, this is a page fault. The page that we are looking for is on the hard disk. So in this case, again, the operating system will first find a suitable entry in the TLB cache where we can bring in the new page table entry. The operating system will invalidate or clear out this TLB entry. Next, it will perform the page fault operation to bring in the missing page from the hard disk to the main memory, just as we have discussed earlier. Once the page is in the main memory, the page table has been updated. After that, we'll update the TLB entry, and then we can restart the faulting process from the instruction which had caused the page fault or the TLB miss to begin with. Note that all of these steps, these are still functionally transparent to the user processes and to the users themselves.